Good day to everyone. This time our topic is diode configuration part 1. For this session, we will explain 4 examples of diode configuration. When you say configuration, it talks about how you connect the diode. Either you connect it in series or in parallel. So let's solve example number 1. It says here we are to find for the value of the current I. So take a look at the circuit. We have a source supply of negative 12 volts. The negative sign is not written since it is understood that the voltage supply is negative. Next, we have here a diode. The diode is actually a silicon diode which is in series with 10 ohms. Okay, so that is our first example. So what is the first step in order to analyze the circuit? The first step is to determine whether your diode is in forward or reverse bias. So this side of your diode is actually the anode, so that is positive. This side of diode is your cathode, so that is negative. So this side is not the cathode, but rather the negative terminal of the supply voltage. So I'm sorry for that. So this is the negative terminal of the supply voltage, which is 12 volts. These negative 12 volts now reverse bias your diode. Okay? So if in any case the diode approximation is not indicated, you always treat or you always solve the problem using the second approximation. Again, if the approximation of diode is not stated or mentioned in a given problem, you always consider the second approximation. So meaning to say, if this is anode and that is negative, the 12 volts, the negative 12 volts reverse bias the diode. So under second approximation, you see the diode as an open switch, okay, if it is reverse, okay, followed by the barrier potential, okay. So this is how you look at the diode, it's an open. So with this, definitely there is no closed path, therefore the current of the circuit or your current I is simply equal to 0. So the answer here is the current I is simply equal to 0 since the diode is reverse bias. Okay, reverse bias or the diode is open. So we have to provide for the explanation. The diode is open. So that's it. Okay, the diode is reverse bias or open. That's the reason why our current in the circuit is simply equal to 0. So that is for example number 1. Let's proceed now with example number 2. For example number 2, this is your silicon. The cathode terminal is here. This is negative, while the anode terminal is here, and that is positive. We have a series of 20 ohms connected with your silicon. And of course, we have a supply voltage which is 20 volts. Now, this 20 volts is actually negative 20 volts. So the first step is to determine whether your silicon is in forward or reverse bias. So as you can see, this is the negative terminal of your supply voltage. It is connected with the cathode. Therefore, the negative 20 volts forward biases your silicon diode. Again, if no approximation is stated or given, you always consider or you always treat the diode under second approximation. So how do we treat the diode under second approximation? So let me just rewrite this one. We are to find or we are to determine the value of your I. So I'll be redrawing the circuit so that the second approximation will be much more emphasized. So we treat the diode now as a closed switch since it is forward bias. And then we also consider the barrier potential since it's silicon, it's 0.7. And then the series resistance of simply equal to 20 ohms. Alright? So this is now your circuit. So I'll be placing now a rectangle with a broken line. Okay, rectangle with a broken line. So this is how you treat now the circuit under the second approximation. Alright? So the diode, remember, the cathode is at this side, no? Kanina, the cathode is at this side and the anode is at this side. So meaning to say, the diode was closed because it received a negative voltage drop. So where's the negative voltage drop? That is the negative and the positive. So it receives a negative voltage drop across your diode. And then, what is the voltage drop? What is the polarity of the voltage drop across your 20 ohms? So the secret here is to look on your supply voltage. If this is the negative terminal and this is the positive terminal, so meaning to say, the voltage across here is positive and the voltage across here is negative. Okay? So, how do we solve now this one? So, what is now our solution for this? Our solution for this is, we apply now the KVL. So, using KVL, we can find for the current along the circuit. So, you may have a different orientation on your KVL, but for electronics, I usually consider the terminal where the loop enters or where the current enters. So we will start now with this. So let me just rewrite now the 20 volts here. Okay? So I will enter first with the negative 20 volts. So my KVL now is negative 20 volts. Then let's me go on now with the loop. Then I will enter the voltage drop across your 20 ohms. And then that is the positive current times resistance. That is now the voltage drop. Okay? Then I will enter now the positive polarity of the voltage drop across your diode. That is positive and that is negative. Take note, this is your whole diode. Okay? So your diode was closed because it has received a negative drop here with respect to the anode, which is positive. So I have here plus. So what is now the potential difference of your diode? That is simply equal to 0.7 volts. And since it is a Kirchhoff's voltage law, all voltages must be equated to 0. So negative 20 volts plus 0.7 volts, that will be 19 volts plus I 20 ohms. Okay? So simplifying now your equation, the negative 19 volts will be transferred to the right side. So what you have now is current multiplied with 20 ohms is simply equal to positive 19 volts. So divide this by 20 ohms, divided by this 20 ohms. Then the current, 20 ohms and 20 ohms will be cancelled out. So what I have now here is 19 divided by 20 ohms will simply give you a value of 0.95 ampere. So this is simply equal to 0.95 ampere, or that is 950 milliampere. Alright? So the value of your current is 0.95 ampere, or that is 950 milliampere. Again, if approximation is not stated in any given problem, you always consider the second approximation. Okay? So we will now proceed with our example 3 and example 4. So for example number 3, we have here two diodes. Okay? So this is now the circuit. We have two diodes that are actually face to face now. So ayan. So we have now a supply voltage of 10 volts. Okay, we have a supply of 10 volts. And then we have here the resistance of 10 ohms. This is a silicon diode and that is also silicon diode. So there is a current that flows through your 10 ohms. So what is being asked in this problem? We are asked to solve for the value of your current I. So we are asked to solve for the value of your I. Determine the value of I. So again, the first technique is to consider to check whether your diodes is in forward or reverse bias. Say for instance, this is your diode 1. So diode 1 this is your anode and this is your positive terminal. So your first silicon is forward bias due to the positive 10 volts. Alright? So this will now be closed. Next, this is negative and that is positive. So what happens? Because of this negative terminal, okay, your silicon diode is actually open. Okay? So meaning to say, if this is now open, your current now simply flows through your 10 ohms. There is no current that can pass through this branch. Only the current now from your supply will now be move or flow through your 10 ohms. So if that will be the case, what is now your current I. So, 10 ohms is in parallel with the 10 volts. So, meaning to say, the voltage across your 10 ohms is also your 10 volts. So, current is simply equal to voltage, 10 volts, divided by the resistance of 10 ohms. So, this is now 1 ampere. Okay? Now, let's proceed now with your example number 4. So, for this session, we will end until example number 4, and then the next video will be part 2, still under the diode configuration. So, for this one, we have 2 diodes. Okay? We have the silicon, we have the germanium, and we have the 2 kilo ohms. Okay? So, we have now 2 kilo ohms. And then we have the voltage output. Alright? So, this is now silicon and this is now germanium. Plus 20 volts. Alright? So, what type of circuit is this? This is actually the circuit for electronics. Once you see this one, it simply means this is a terminal. At this terminal, the positive terminal of your supply voltage is connected at this. And where is the negative terminal? It is understood that it's connected to the ground. Okay? So, you can even not write the negative terminal because it is understood that the negative terminal is at the ground. Next, what does this mean? It simply means that the V output is measured from this point with respect to the ground. That's the meaning of this one. So, here, we are also asked to find for the value of your current. So, determine the value of I. So, that is now the required for this problem. So, if we're going to look at the circuit, it is understood that the negative is located at the ground. So, this is ground and ground. So, this is just a closed loop. Remember, we are in electronics, and in electronics, as much as possible, we consume less space. And that's the reason why our diagram, as compared with electrical, is much more compact as compared with the electrical circuit. Right? So, let's solve now the current for I for this circuit. But first, we have to consider whether your diode is in forward or reverse bias. This is your anode, and that is positive, so your diode is forward bias. This is the anode of your germanium, and that is your 20 volts, so this is also forward bias. Okay? So, meaning to say, the silicon operates, germanium operates because it received a positive voltage. What about the polarity of the voltage drop across your 2 kilo ohms and another 2 kilo ohms? So, since this is your supply voltage, the voltage drop, this will be positive and that will be negative. This will be positive and that will be negative. So, that is now the voltage drop across the 2 kilo ohms. So, let's find for the value of I. So, this is just one of the requirement. Okay? So, we can follow up with what is V out. So, what is V out? So, VO is actually V out. Okay? So, let's have the solution for this. The solution is using a KVL. So, we enter the loop, which is we enter the loop now. Where do we enter? It is understood that the negative is at the ground, so we enter the negative. Negative 20 volts. Then, this is under second approximation. You consider the voltage here, which is 0.7 volts. Okay? Plus the needed voltage of the germanium, which is 0.3 volts, plus current I multiplied with 2 kilo ohm, that is simply what? Voltage. Plus, common factor is I. So, I times another 2 kilo ohms. So, I factor out your I. So, all voltages must be equated to 0 because that is the principle under the KVL. So, what is now the value of your I? So, negative 20. 0.7 and 0.3 is 1. So, negative 20 plus 1, that will give you a value of 19 volts. Plus, I, 2K and 2K, that is simply equal to 4K, equated to 0. Therefore, what is now the value of your I? I is simply equal to what? 19 volts divided by 4K. Or, if you're going to look at your calculator, that will be 19 divided by 14,000. that will be a 1.36 milliampere. 1.36 milliampere.